Alright, the topic today is inverse functions. We'll be looking at what they are, how do you get those things, what do they mean compared to the original function, what the relationship is, how do they look differently on a graph, and then how do you find one, how do you write one given the original function. So this video is about 13 minutes or so. I think that we'll be able to explain things pretty well here. So I'll start with the definition of an inverse function. The inverse of a function, and we'll call that function f to start, is defined as satisfying the following expression. Now this expression is probably going to be a little bit confusing, but I'll do some examples with it when we're done, and hopefully it'll make sense as you watch it or as you see what I'm doing. To better explain it, I guess. So we're building on the idea of composite functions from yesterday. So if I take my inverse function and I plug it into my original function and evaluate that, I should be able to get x for an answer. Same thing if I go the opposite way. And it must work in both cases. So here's our example. Take a very simple linear function to start, 2x plus 3. What I want to do with this now is I want to select a couple of x values. So I'm just going to try to find some points, basically. So pick any x values that you want, and then solve for the corresponding f of x or the corresponding y. So the first value I'm going to plug in is 1 right now. Take 1, plug it in. 1 times 2 is 2. 2 plus 3 is 5. So 5 is going to be my f of x, or my y for this. If I wrote that as a coordinate, it'd be 1 comma 5. Do the same thing as I plug in 2, and I get 7 for that answer. So I have 2 points right now, 1 comma 5 and 2 comma 7. So using those 2 points and what we learned back in algebra, I can take those and write a new equation after I swap the x's and y's. So what I'm saying is, instead of having 1 comma 5, that is going to now become 5 comma 1. My x has become my y, and my y has become my x. I'm flip-flopping the domain and the range for these two functions. Remember that. That might be important later on as we graph these. After I swap those x's and y's, like I mentioned earlier, I'm going to go ahead now and find the new equation. I need to find slope, and then once I find slope, I need to go ahead and find the y-intercept. I'll be quiet here for a second and let you watch that work. If you notice, I got a little mistake there. That should not be 2 over 2, but it should be 1 over 2. So that's going to actually change some work here. In a second, I'm going to erase a lot of this and go back and correct that mistake. That wrong slope is going to actually change everything in my problem. Alright, so that's really 1/2 now. And so that's going to change the slope that I plugged into my slope-intercept form. Sorry for the mix-up on this. Still doing the process the same way. Now as I subtract that 5 halves, I'm going to get a negative 3 halves now. And so my final function is going to be 1/2 x minus 3 halves. This is the inverse of my original function. Now, do you believe me? Do you believe that this is really the inverse? If you don't, then we can go ahead now and use this with the definition that I gave you to start this to determine if it really is. Remember, what should I be able to do? I should be able to take this inverse function, plug it in for x in my original function, and when I simplify that, it should equal x. Same thing should happen when I take my original function and I plug it into this x. I should be able to get that as well. So here we go. Let's verify that right now. So again, what does that say? It says take my inverse function and plug it in to my original function. So that's going to be 2 times 1/2 x minus 3/2 plus 3. I forgot to write the plus 3 down right now. I'll write it down here in a second. So use distributive property on that. 2 times 1/2 of x is 1x. 2 times a negative 3/2 is negative 3. Now I'm remembering. Got to put that plus 3 in there at the end. Add that together. Those 3's are going to cancel out, and I have an answer of x. So far, so good. Now I'm going to check it out the opposite direction now. I'm going to take my original function and plug that into my inverse function. So anywhere I see x in my inverse function, 2x plus 3 is going to go in its place. Distribute that out. Half of 2x is x. Half of 3 is a positive 3/2. Minus 3/2. Those are going to cancel out. And my answer is again x. So this is a test or verification, if you will, that 2x plus 3 and 1/2 x minus 3/2 really are inverses of each other. So with that idea in mind, with that kind of working definition there, let's go ahead and take a look at what the graphs of these would look like. So if you're graphing inverse functions, what might you notice about them? What might you be able to see as you're working on them? And maybe you'll graph them before you do any algebra work and be able to tell right away whether it's an inverse function or not. So this is just a different way to look at inverse functions. Instead of algebraically, we'll look at it graphically now. So we'll start by putting in a couple functions that I know are inverses of each other. The one that we just did, that's too many plus signs there. How about 2x plus 3 and our 1/2 x. I think I forgot what it was again. There it is, 1/2 x minus 3/2. 1/2 x minus 3/2 is what I want. Sorry about that. Technology is great, but slows me down a little bit right now too. So as I graph those right now, there's the original function. There's 2x plus 3. There's the second function, 1/2 x minus 3/2. And what do you notice about those? Not much? Okay. Let's try another one then. X squared. Now x squared doesn't really have an inverse. I'll explain why in a second, but you can see part of what I want you to see here as we put in the inverse of x squared, which is the square root of x. I'm actually going to put in the square root of x, and then I'm going to put in the opposite of the square root of x, just so you can kind of see a little bit of the picture here. Again, what do you notice there? Is there anything that you notice at all about those two functions? And again, I'm using functions kind of loosely right there because those are not all functions. We'll talk about that down the road. Alright, one more. I'm going to put in x cubed, and I'm going to put in the cube root of x. Now these are both inverse functions again. They are inverses of each other. As I graph them, what do you notice? So after all of that, I hope that what you see is that an inverse function, or a function and its inverse function, are reflections of each other over the line y equals x. Again, you could rewind this right now if you wanted to. Go back and look at those graphs again and see it for yourself. See that those are reflections over that 45-degree line, that diagonal line, y equals x. So if you have two functions and you want to know quickly if they are inverses, a quick peek at their graphs might help you. Also, it might be verification, just to know for sure that they are. So last thing what I want to do right now is I want to give you 4 steps for finding the inverse of any function, or any function that has an inverse, algebraically. 4 steps, pretty easy steps I think, as long as your algebra skills are fairly solid, to do this for just about any function. So the first step is, does the function have an inverse? It's a good question. If it doesn't, then all the rest of this work is really not very useful. The way that we will determine that is by using something called the horizontal line test, very similar to the vertical line test. The horizontal line test says that if I draw a horizontal line anywhere across my original function, and it touches that function in more than one spot, then it does not have an inverse. If I can draw horizontal lines anywhere on there and it does not cross at any more than one spot, so only touches the function at one spot, let's say, then it does have an inverse. Here's 2 pictures of them. That's your basic x cubed function. You notice that no matter where I draw those across, only touching in one spot. However, if I put up the quadratic, your basic quadratic function, your parabola, you can see that right there I cross in 2 locations. So most quadratics will not have an inverse. So once we've determined that our function does have an inverse, what we're going to do is very similar to what we did earlier. We're going to do some flip-flopping with our y's and our x's in order to figure it out. So what we'll do is we'll start by writing our original function. And since f of x and y really mean the same thing, we're going to write it with y equals instead. Once we do that, we're going to swap the y's and the x's in the function. So anywhere you see an x, you're going to put a y in. And anywhere you see a y, you're going to put an x. Again, this is very similar to what we did earlier when we were trying to determine that original function's inverse. And then lastly, we're just going to go ahead and solve for y now. When we solve this for y and we get y by itself, that answer will be the inverse of our original equation. Now that you've seen this process, let's go through 1 or 2 examples so you can see the process here. If you want to try this on your own, feel free to do that as well. Our original function, a rational one right now, is 5 minus 3x over 2. Again, you should check that first, make sure it does pass the horizontal line test. Once you do that, write it with a y, switch those x's and y's, and now start solving that. I know I'm going pretty fast through this, so feel free to stop, rewind, listen more than once if you need to, so you can understand how I got y equals negative 2/3 x plus 5/3. That is the inverse of the original function. I'll be a little quieter on this next example so that you can kind of see for yourself how to do that. Do you notice anything that I forgot to do in this problem? Like, let's say, check to see if it really does pass the horizontal line test. You'll notice when I get to this point right now, I actually have two functions at this point. This function did not pass the horizontal line test. Does not have an inverse. Again, you can see a picture of this graph right now. As you graph that, as you would, I'm sure, realize that parabola is not going to pass the horizontal line test. And so all that work I did really was for naught. Alright, last one. Again, you might want to pause after you see this function. It's the cube root of x plus 1. Go through that. See if you can do that yourself. You get that same answer I did? That is the inverse. So, hopefully you'll get a little more practice on this. I think that as you do a few of these problems, it will make more sense. But I do think that you do need to practice to get a little bit better at it. I hope this helps. I will see you next time.